Gentlemen, welcome to our physics lecture class, and in this class we are just going to do our part 1 on work, energy and power, just like we always do it. For part 1, normally we focus on the theory side of a topic, and then part 1 going forward will normally focus on applications and calculations. So before I move on, can someone kindly confirm if you guys are able to get me or not? Are you guys able to get me? Alright, thank you. So we'll look at work, energy and power. So the first thing, we are going to look at what is work done. So when you look at work done, the work done by a force is defined as the product, as the product of the force and and the distance. So it is just the multiplication of a force and and the distance. In short, we are saying work is equal to force times times the distance. But one thing that you need to understand is that this force might act at a given angle, and you know that a force is is a vector quantity. So you have to put it in mind that in as much as you work on finding the work done by a given force, you also need to consider the angle at which a given force is acting on. So I'm going to explain much about what work is, the formula to use, and some few applications which I'll explain in part 2 and other parts which I'll do on this same particular part. So work done can simply be written as W is equal to F cos theta, and then S is just the displacement or the distance. So that's the basic formula for work done. So work can only be done when there is a distance that has been covered by that object on which the force has acted on. Okay, so this can simply be represented by that animation. So work done is just equal to the force times the distance, the force times the distance. So if you look at that particular animation, one thing you can understand is that this particular individual has moved the box, has moved this box at a certain distance, and this person has applied the force. So if you look at the formula of work done is equal to the multiplication, the product of this force cos theta. The theta is just the angle at which this force is acting on, and then multiplied by the displacement or the distance which has been covered. So with this in mind, we can say from the formula, W is simply representing work done, and then when you look at F is just representing the force. So W is representing the work done, F is representing the force acting on an object, and then S is the displacement, and then lastly theta is just the angle between the force and the displacement. It is the angle between the force and the displacement. So if you look at this object, this force is going this side. In terms of animation, this is how the force is. So the distance which will be covered, it is this particular distance here. So this distance, when you look at the distance is having an angle with the force. So this angle which is existing here, which is theta, is the one that we normally consider when finding the work done by the force. So the theta, which is the angle, is just between the force and the displacement vectors. The force and the displacement vectors. So work is normally a scalar quantity. Work is normally a scalar quantity. So when you talk of a scalar quantity, that simply means that there is no direction. There is no direction. So meaning this guy has only what? Has only the magnitude, which is the same as the what? The size. Okay, and this magnitude has a what? A number, and the what? The unit. So these are the only two things that you need to understand when you are trying to represent the work done. So work is a scalar quantity, like I have already stated. It's not a vector quantity, but what we are multiplying are simply vectors. Okay, so if the force and the displacement are in the same direction, that simply means that the angle will simply be what? 0. So if the force and the displacement are in the same direction, okay, we are referring to a situation where the force and the what? And the displacement are in the same direction. So that simply means that there is no value, or there is no angle in between them. So in such a case, you need to understand that the theta, which is the angle, is simply equal to 0 degrees. So cos 0, when you plug in on your calculator, cos 0 when you plug in on your calculator is simply equal to 1. So in such a case, the formula tends to be simplified. So let me just show you how it's going to be simplified. So work done will just be equal to force times the distance, or W is equal to force times the displacement or distance. This is only in a case where the angle is what? 0, and the force and displacement are in the same direction. A good animation I can give is this particular animation. So if you look at this particular animation, the force, which is 12 Newton, and the distance, which is 5 meters, they are in the same what? In the same direction. There is no angle. If you look at the first animation and the second animation, there is a big difference. The difference is that the first animation is acting at an angle. There is an angle between the force and the displacement. But for the second animation, the force is not acting at an angle. As a result, you need to understand that since there is no angle, which is just a 0 degrees, so cos 0 is just simply 1. So if cos 0 is 1, then that means that the work done can just be said to be equal to force times the displacement. With that being said, you need to also know how to define work. Remember, here we are talking about work done. So work can only be done when there is a distance that has been covered. So work is just the transfer of energy from one entity to another by way of action of a force. So there is a force which is needed, and this force is applied over a certain what? Distance. So work is the transfer of energy, So in most cases, work and energy are being treated as the same thing, but not always. Work and the energy are normally treated as the same thing, but not always, because you find that in some object the energy can be transferred, but you won't see any distance which has been covered. In some cases, the energy is transferred from maybe potential energy to kinetic energy, but you won't see any distance that has been covered. Okay, so with this being said, let me move on the next part, and then I'll allow you guys to ask questions. So for work to be done, there should be a distance that has been covered. That's a very important statement that you need to understand. So for work to be done, you need to understand that there should be a distance that has been covered. Okay, now if you look at the animations here, all these animations that I have shown here, there is work that has been done, because all of them, they are trying to move the object or themselves at a certain distance. So if you look at this first animation, the first guy here, the yellow guy, this has to be Florence. So let's treat this cartoon as Florence. So when you look at Florence, she's trying to push this box. So as she tries to push this box, she's applying a certain force. Okay, she's applying a certain force. So because that force is making this object to move, you can see she's moving there. So okay, since it's a she, let's try to give her some hair. Let's try to give her some hair there so that she looks nice. And I'm sure she deserves some hires. Yeah, let's quickly look for the hires for Florence. There's the eye there. Okay, I think we need a black spot. Where is it? There you go. So if you look at this cartoon here, it's trying to push this guy. So for work to be done, this has to move. Okay, same applies to here, this man here. It can be Uncle Bernard, who loves normally who loves doing some gym. So for this person to show that the work is being done, there is a distance covered as he is trying to put or to push this, to lift this thing up. So there is a distance which is being covered, and this distance is making the work to be done. Then jumping here, there is also work done. This guy, this has to be a sugar daddy here with a kapot belly, trying to enjoy himself during hot season in October. That's for Zambian weather. So this man is throwing himself and jumps into a swimming pool. So in reality, this person might not know that there is some work which has been done here. Why has the work been done? Because he's able to change the energy from potential energy to kinetic energy. So in most of our daily activity, we do work in most of our activities. We do work even without realizing it. So long energy has been transferred, then work has been done. Okay, so long energy has been transferred, so long energy has been transferred or changed, then work has also been done. Okay, so let's quickly look at some of the things that we need to understand. Let's look at the units of work. So work is the product of force and the distance. So the SI unit of work is just the what? Is just the meter multiplied by Newton, which is called the what? The joule, and it is simply represented by J. Please take note of the SI unit. So in the exam, you might not be given you might not be given the work done, or maybe the temperature, or maybe the 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 distance, but they might use the units to ask you identify which one is a scalar quantity and which one is a vector quantity. So joule is the SI unit of the work done, and when you look at joule, 1 joule is the work done by a force of 1 Newton, okay, a force of 1 Newton when it is displaced a single meter, okay. So that's the definition that you need to take note of when you are trying to define work. So work is simply it's simply measured in joules, and when you talk of a joule is the work done by a force of 1 Newton when it displaces an object 1 meter in the direction of the force. I think that's it for this part, and I can allow you guys to ask questions. Do you guys have any question? You can either unmute yourself or you just raise your hand. Any question?
No question at the moment, sir.
All right, thank you. So let's quickly move on and look at the other things that you need to consider as you study work, energy, and the power. Now, energy is a measure of the change imparted to a system. It is given to an object when a force does work on the object. In short, what we are trying to state here is that work and energy are just the same thing. Work and energy are just the same thing. So work done and energy, they are more like the same thing, but not really the same thing, because energy can be transferred without any distance observed. Energy can be transferred without any distance observed, but at the same time you are going to understand that the work done, which is the work done by the overall object, it is equal to 0 when in the actual sense inside that particular object there are moving particles which are doing some work and transfer of energy. So we'll try to understand the work energy theorem later on, and I think I'll also give you an assignment to go and study more on what the work energy theorem is all about. So the amount of energy transferred to the object, it equals the work done. The amount of energy transferred to the object is equal to the what? To the work done. That also simply means that the amount of energy which has been lost by an object is also equal to the what? To the work done. Because energy can be what? Energy can be gained or lost. Energy can be gained or lost. And it can also be transferred to another form of what? Energy. Okay. So when energy is being transferred to another form, that energy which has been transferred, it is what we equate to what? To the work done. So like I have already stated, the work done by an object, it is also equal to the amount of energy that has been lost. So when energy has been lost, then the work has been done. When energy has been transferred, the work has also been done. When energy has been gained, the work has also been done. Now, work done and energy, they have the same units, which is what? Joule. This simply means that work done and energy, they are both what? Scalar quantities. So energy is also a scalar quantity. We have different types of energy. There is heat energy, electrical energy, kinetic energy, potential energy, and so many types of energies. But in this particular part, we are not going to look at all the types of energy. Instead, we'll just look at the translational energy, which is known as the kinetic energy, and also the potential energy, which can also be said as the gravitational potential energy. So in this particular lecture, those are the two energies I'm going to give as examples. Electrical energies and other types of energy, you are going to discuss them later on. But one thing I need to emphasize on is energy and work done are scalar quantities. They do not have a direction. They do not have what? A direction. But they have a size, which is the magnitude. Okay. So an object, because we are saying energy and work done are almost the same, that simply means that an object that is capable of doing work, possesses what? Energy. It has energy. Any object that is able to make work to be done, it has what? Energy. Now, let's quickly move on and look at the animations below. So, there are two animations here. There is a car which is moving, and there is also a boy who is running. Both of these animations are showing one important thing, and this important thing is what? Is energy. Both of them are having energy. A very good example of energy which you can give here, it is what? Translational energy. Translational energy is also known as the kinetic energy. So for you, my colleagues, you can use kinetic energy, but in the exam or test, sometimes they might use linear translational energy. Linear translational energy. Okay, because we also have angular translational energy. So in the next topic, we are going to do momentum. After momentum, we are going to look at angular motion. So under angular motion, that's where I'm going to discuss angular translational energy. So this particular animation is just showing about energy in motion, and this type of energy in motion is known as what? Kinetic energy. Now, kinetic energy is a very good example of energy, and this type of energy is the energy which an object possesses when it is in motion. When you are running, when a dog is chasing you, both you and the dog, you are having kinetic energy. Okay? Even when a car is moving, you are enjoying a ride, that car is possessing kinetic energy, including yourself who is in that particular car, because you are moving at the acceleration which is equivalent to the acceleration that a car is moving. So if a car is moving at 70 km per hour, you are also moving at that particular per hour squared, you're moving at that particular acceleration. Same applies with the velocity. If the car is moving at 7 meters per second, then you're also moving at 7 meters per second. Those things were explained in part 1 of Newton's laws of motion. But here I've just given an example of energy, which is the kinetic energy. And this type of energy is the energy which an object has when it is in motion. So kinetic energy is also known as linear translational energy. There I've just put translational energy, but it has to be linear translational energy. So linear translational energy is also known as the kinetic energy. The formula is simply Ke is equal to half mv squared, where m is what is the mass and v is the velocity. Ladies and gentlemen, let's put these guys in mind. Let's put these guys in mind, because this part is going to be applicable when we discuss momentum and when we also start discussing angular motion. But because there you are going to be asked to find the translational velocity before the thing slides and many other stuffs. So it's a build up of the future. So this is the formula of kinetic energy, which is half mv squared, and this is the energy which a body has when it is in motion. So when m is in kilograms, so the m is the mass. So make sure that as you make calculations, the m has to be in kilograms and the velocity has to be in meters per second. So the SI units of kinetic energy are just simply what? Joules. So please take note of that. Let's quickly move on and look at another type of energy. So basically this young lady is enjoying the, I don't know what this thing machine can be called. Yeah. So as this person is riding this, is carrying this ball. Okay, if you look at the brown ball here, this brown ball is stuck at one particular position with respect to the height. Let's say this is the height with respect to the height. So the type of energy which this object is having, it is what we are calling the what? The potential energy. So the gravitation potential energy is the energy possessed by an object because of the gravitational interaction. So this gravitational interaction is due to the pull of the earth on an object. It's due to the pull of the earth. It's due to the pull of the earth on an object. So when the earth is pulling that object, then it's causing the object to have a type of force which we are calling the what? The weight. We talked about that when we were discussing on Newton's laws of motions. So the pull of gravity of the pull of the earth on an object, which is the gravitational force, it is the one which leads to the what? To this type of energy, which is known as the gravitational potential energy. So in so doing, we have to understand that this energy depends on the height. Okay, it depends on the height away from the zero level. So this guy can be represented by mgh. That's the formula. Remember, mgh, this part here, it is just equivalent to the what? To the weight. It's just equivalent to the weight. And then you have the height in meters. So you have the height in meters. So the gravitational force, gravitational potential energy, it depends on the height. Okay, so when the height is high, you have more gravitational force. Now look at this. Look at this realistic example. Why is it that when a person falls from a rooftop going down, they will surely have their bones broken, or in many cases they might die? Okay, so when a person is from a rooftop and they try to jump, they will surely die. Why? Because they are far away from the earth. They are far away from the zero level. So that gravitational energy, it will be converted into kinetic energy. By the time they are reaching there, they'll automatically be broken due to the impact. Now, you carry a person like someone or anyone else. They jump from the bed and they jump down. When they jump down, they'll automatically be okay. Why? Because the potential energy due to the height is what? Is low. So I've given two and a good example. One, a person who has stood or jumped from the rooftop, the buildings of a university, and then they fall down. They will surely break their bones, or in most cases, they will surely die. But if the same person was to jump from the bed and jump on the floor, they will not have any injury of any type, unless maybe they had some problem in landing. Then they can have a dislocation and no death will be recorded. So that's how you can see how the potential energy depends on the height at which something is. So potential energy, it's relative to the height, and this is due to the force of gravity acting on it. So that's the formula of potential energy, which is mgh, where g is the acceleration due to gravity, which varies. It can be 9.81, in other books it can be 9.8, in other books it can just be 10. So make sure that you check the units and value given. So notice that mg is the weight of the object. Mg is the weight of the object, which is the same as the force, because weight is also another example of a force. Okay, so with this being explained, I would allow you guys to ask questions if you have any questions. Do you guys have questions? Any question? Given, do you have a question?
No, sir, I don't have.
Okay, Haggai, any question?
No, sir, I'm okay.
Okay. Ruth, do you have a question? All right. Okay. Let's quickly move on and look at the other parts that you need to take note of. So the SI units of gravitational energy, just like kinetic energy, is just the joules. So when work is done on a point or a rigid body and there is no change in potential energy, the energy imparted can only appear as kinetic energy. So insofar as body is not rigidly, however, energy can be transferred to its part and the work done on it will not precisely equal its change in kinetic energy. I think this is where we are now talking about the work energy theorem. This is where we are now trying to explain that energy and work done cannot really be equal to each other. So I'll give you an assignment to go and find more about the work energy theorem. So please go and find out about the work energy theorem. So that will be your assignment as of today. Okay, so conservation of energy, that's one thing that you need to take note of. So if you look at my animation there is this guy who is enjoying a ride. So the person was on top and then he had to slide. So one thing you are going to observe is that when this individual was on top, he had potential energy. When it starts to move, it will have what? Kinetic energy. So according to the conservation of energy, energy can neither be created nor destroyed, but it can only be transferred from one kind to another. So one thing that we can understand from here is that from the time of creation, energy has remained constant. From the time of creation, energy has remained constant. The only thing that has been happening to energy is it being transferred from one form to another, because no one can create it and no one can destroy it. So if something cannot be created, if something cannot be destroyed, that simply means it has been the same way. So since the time of creation, energy has been the same. So one form of energy, according to some theorem, a very good example is mass. Mass is also said to be another form of energy because it cannot be created or destroyed. That's according to some theorem. So like if you look at the animation here, the energy which this individual had when he was on top, it was potential energy. That potential energy was not destroyed. Instead, it was just transferred from potential energy to kinetic energy. So that's conservation of energy. The last part, ladies and gentlemen, we can look at is power. So let's quickly define power. What is power? So power is just the rate of doing work. The rate of doing work. So in short, when you talk of something that having a rate, that simply means that there is an application of what? Of time. Okay. So the rate of doing work is what is said to be power. So when you talk of power, it simply means that it's depending on the force, the distance, and also the time. Work done is equal to the force and the distance. But power is equal to force times distance, which is work done, over the time which I've put that side, which is changing up to 3 seconds. So work done, average power is just simply equal to work done by a force over time taken to do this work. And the other way which this work done can be said is equal to force times the speed. Force times the speed. So those are the two equations you can use to find power. I'm going to use these two equations in my part 2 and part 3 and other parts of work energy and the power. So average power is equal to work done by force over time taken to do this work. but there is also another formula, which is average power is equal to force times the distance. So the speed is measured in the direction of the force applied to the object, and more generally, power is just the rate of transfer of energy. So that's another definition you can give to power. Okay, the SI unit of power is simply watt, which is normally represented by W. Okay, thank you very much guys for joining me. In the meantime, I'm going to allow questions from you guys. But for those who have questions, or you will have questions after watching the class, you are free to WhatsApp me on those lines and I'll be able to respond. So in the meantime, I'll allow you guys to ask questions.